All right, welcome back to track one. We're here with Sam Newman, and in a break from scheduled programming, Leon and I are presenting this one together, and there's a very specific reason for that, which we're going to get through in about 30 seconds. Vote in the chat. Who looks better dressed as Alice? Go. All right, that's all you're going to see. We're running out of time. So, quick shout out to the sponsors: Packet, Container Solutions, Rancher, OfferZen, CNCF, Honeycomb, Aqua Security, Kinfolk, Giant Swarm, and CloudBees. You can go and speak to them all in their sponsor rooms. I think that's it. I think we just kick it off with a quick round of applause. Go for it, Sam.
Oh, I'm clapping. I'm clapping for myself.
Yes, exactly.
Virtual applause. I thought there was going to be like a canned applause and then a canned laughter track, but this is it. Apparently.
Yeah, I thought so too.
I lost it.
Oh, in more ways than one, you've lost it.
Okay, here we go.
That's pretty bad.
Yeah.
All right. It's yours, Sam.
All right, I'll take it away, shall I? Okay, well, thank you so much for coming along. Just in case you can't quite see, I am indeed wearing rabbit ears. Carla made me do it. It's sort of blending in with my virtual background, which actually is a picture of near where I live. We did discuss me presenting it from the woods, but we realized logistically it was going to be challenging, not to mention at this stage, kind of borderline illegal as well. I'm going to be talking about microservices because that's what I do and I've got to pay my mortgage, but really looking at some other aspects of microservice architecture. We're not talking about the technology so much as some of the concepts, and really concepts that have been around for a very, very long time that we sometimes ignore. I wrote a book years ago called Building Microservices. I'm working on a second edition at the moment. But I most recently finished a book called Monolith to Microservices, which is a book all about how you break big systems down into smaller pieces. Information about that is available over on my website, and you can get it now. It's even being made into an audiobook, which I suspect will be one of the most boring audiobooks ever conceived by man, but there you go. So we're here to talk about microservices, as always, and one of the main properties I've been talking about for a long time as being super, super important in the realm of microservice architectures is this concept of independent deployability. So I've got a call service. I go to my account service. I didn't pick a call service. I picked the account service. And I decide that I need to change it in some way, shape, or fashion. I want to make a change to that, roll out some new functionality. This property of independent deployability basically means that I should be able to make a change to that service and deploy it into a production environment without having to touch anything else. And that's a great idea. And when you can pull it off, it works fantastically well. But there's a lot of detail in terms of how we make this work. There's lots of technical aspects. If you want to look at things like zero downtime deployment and isolated execution environments, all of which can help make independent deployability a thing. But a lot of it starts with how we think about the connections between things. And I don't mean the network protocols. I mean sort of almost the logical semantic connections between these things. If we think about these interactions, if I want to be able to change a service that's being used by something else, so in this situation here, I'm changing the account service, I need to maintain compatibility of any consumers of my endpoints. If I want to have that independent deployability, I have to maintain compatibility. My interface of my service has to remain somehow stable. If I make a mistake or if I break that interface in some way that's backwards incompatible, when I come to deploy my microservice, I'm going to break people around me. So working out how we define our service boundaries in order to make independent deployability a possibility, that's a really important aspect of microservices that I think isn't always talked about enough. And I think part of the reason we don't talk about these ideas enough is because a lot of the ideas behind how you find these boundaries are actually quite old ideas, and we tend to look down our nose at old ideas. So I'm going to take you back into the dark mists of time, back when we used to build systems primarily on things like this. This is a mainframe. So we used to have a very small number of very large computers. These were the mainframes. Most of our software was written to run on these big machines. You'd go into a bank and they might have one big mainframe for virtually everything. Most of the software that was sort of running on it would be now what we would consider to be monolithic in nature, although that's not, strictly speaking, entirely true. But over time, as computers became more powerful and we found out more reasons to do things with our computer programs, the programs themselves got bigger and bigger and bigger. And we needed ways to organize all of that code to make it easier to work on. And this is where things like modules came from. So the idea behind modules is that you take a big program and you can actually break that program up into lots of little modules that work together. And these modules could contain different pieces of functionality. And these modules could be worked on by different teams. This is also how you help scale up delivery organizations, right? So one team could work on module A different team could work on module B. These modules, because you can kind of link them together, and or also a portion of reuse. So I could take a module that I'd use in one application and use that somewhere else. Now, back in the days of mainframes and sort of single process monolithic systems that we use today, all of these modules are packaged together in a single instance, really, or process. Mainframes have different topics and different concepts. But this idea of a module as being a sort of firm boundary within our systems has become quite weak over the last 20 years. The concepts of modules have been around since the mid 60s in some way, shape, or form. And we theoretically have the capability to build modular software in our current modern runtimes, but the concepts around modules tend to be quite weak. We think of things like packages in Java or namespaces in .NET, and we think of them more just as a way of categorizing and organizing code, whereas theoretically these things give us the capability to create proper modular boundaries. Where we really encounter things that are closer to maybe the original ideas around modules is where we start reusing code from other people. We're putting down jar files with Maven or gems of open source code. When it comes to reuse, we think about packaging something up with a well-defined service, well-defined sort of module interface that we then include in our programs. But we don't often think about taking our own code and breaking it down into modules. And indeed, many of us have development tools that actively go out of their way to violate modular encapsulation. IntelliJ pops up and says, "Oh, this symbol you're trying to use isn't visible from your sort of scope. Do you want me to change its visibility level?" I used to do this when I programmed in C++. I discovered that with a single macro def, I could alias the private keyword as public, which meant in a code base, wherever you saw the word private, it would actually mean public. And that showed how much I knew when I was in my 20s. So if you think about modular software, it's about breaking things apart into modules that can be worked on independently and theoretically reused in different ways. And this sounds quite familiar. Roll on a few decades and we move into the world where we now have, rather than having a small number of large machines, we now actually have a large number of, relatively speaking, small machines. We now have data centers with hundreds of physical, thousands of physical machines running in them. Those machines are in turn virtualized. We have a lot more computing power at our disposal. And so that shift really from sort of the mainframe machine through mid-range into what we now think of as our current modern server architecture meant that we had a lot more computers on which to run our software. This then led us to thinking about running our programs across multiple computers. We can think of microservice architectures as arguably a form of modular decomposition. We've taken a system, we've decomposed it into groups of functionality. It just happens that these modules, what we now call microservices, are running on different machines. The communication between those modules is now going over network calls rather than going within a process boundary. So that has all kinds of nasty problems as a result. And this is a really interesting way of looking at the world. And sort of, I've only really come to it in the last sort of 5 years or so as thinking of it in this way. What this means is that, yes, we can learn an awful lot about the world of distributed systems to help us build our microservice architectures, but we should also be learning as much about the world of building modular-based systems. And work has been done in this space for decades. But fundamentally, if we get these ideas right, it should make it easier for us to do independent deployability, because we can find out how to get our module boundaries described in a way that allows for them to change easily. One of the earliest ideas that sort of has a special resonance in this space is a concept called information hiding. This was originally developed by David Parnas back in 1971. And he was looking at, well, if we're going to create modules, how do we define module boundaries that make it easy for us to work on these things independently from each other? He was looking at, a team working on one module, a different team working on another module. how can we kind of define the boundary in such a way that we get some degree of independent working? The idea being, if we can make that happen, you can add more developers to a project without them all getting in each other's way necessarily. So this concept of information hiding is what he zeroed in on. And indeed, information hiding then has gone on to inspire lots of other things, like what we now think of as encapsulation in our object-oriented programming languages, for example. Now, I'm not the first person to have this sort of epiphany, the linkage between information hiding and our microservice architectures. Agent Collier was there before me. So he writes a blog called The Morning Paper. And a few years ago, he went back and looked at a lot of David Parnass's original work and said his ideas actually stack up really well in the microservices world. When we think about information hiding, what do we mean? Well, let's take a microservice here. This is the accounts microservice. I told you I'd start with something sexy and cool. And I've got the shipping service out there that wants to gain access to bits of my functionality, maybe bits of my data. Now, if we allow that service to just reach straight into my internals, we sort of have a bit of a problem here. Because then if I try and change, if I'm someone that's working on the account service and I try and change some of those internal implementation details, if the external party is using those internal implementation details, when I make an internal change on my service, I'm going to break the external consumer. And this is a problem. This is where we have problems around things like backwards incompatibility. I'm making innocent changes as a developer to a service without realizing that some outside party depends on that particular implementation detail. And when we have code bases that don't really separate the idea of what is shared and what is hidden, this problem comes up a lot. With information hiding, the idea is we hide as much stuff as possible and that we're really clear about what are our secrets. What are the things that we don't want anybody else outside of our module boundary, or in our case, our service boundary, to see? As a developer, I want a really clear idea that this stuff here, this is mine. I can do whatever I want with this. I don't have to worry about anybody else changing it because they can't see it. And I want to say these things over here, this is this stuff which is explicitly exposed. This is the interface that I expose to the rest of the world. This is my well-defined surface interface. As long as I make sure that that thing stays the way it is, then I'm not going to break anybody else. I just have to make sure that my outside consumers of my service only access that sort of allowable part of my service boundary. The stuff that I've decided to share, these could be, your methods that you're exposing on a gRPC endpoint. These could be the resources you're projecting if you're building, say, a REST-based system, or the events that you're emitting if you're building an event-driven system. But by being very, very clear about what is shared and what is hidden, you're going to have a much easier time of knowing what you can safely change without breaking something else. But you do have to think carefully about this. And in general, when it comes to information hiding, it's much easier to expose information later on than it is to hide information you previously exposed. So hidden things can change, shared things can't. So just remember, what are the things that I can't change? What are the things I can? If that isn't clear to you working on a microservice, you're going to have a bit of a problem with it. Being explicit about what is shared is one reason why I'm such a big fan of schemas. I used to be a bit anti-schemas because I had spent years dealing with things like WSDL and all this sort of stuff. But the reality is that having a schema for your service interface, be it an evented endpoint or some kind of synchronous API, at least gives you some degree of explicitness about what your service exposes. You can say, this is what I allow to out. That is useful for clients of your service because they get sort of a programmatic definition of what they can do with you. But it's also useful for you as a developer working on that service because as long as I don't make any change in that schema, there's a good chance I'm going to be okay in whatever changes I make. I've glossed over a few details there, but schemas for me are like typing. Yeah, when I think about programming languages, if I have a statically typed language, the compiler is going to catch a lot of my problems. If I have a dynamically typed language, I'm mostly going to catch a lot of those problems using tests. So I can call a method that doesn't exist in a dynamically typed language. I'm only going to realize that at runtime. So I use tests to catch those things up. With a statically typed language, if I try and call a method that doesn't exist, the compiler is going to tell me. We can do similar things with schemas. If we have schemas, it's not going to catch all backwards incompatible changes, but it's going to catch an awful lot. And there's a lot to be said for improving our workflow around how we work and use schemas. So another old idea is sort of the world of structured programming. Some of you may have learned about this at university. This was work done by people like Larry Constantine and Edward Jordan, looking at how do we take computer programs and sort of take some of these ideas and think about modules in a bigger sense. How do we create software which works at a larger level of scale? Out of the work of structured programming come two terms that we use an awful lot, especially in object-oriented programming, but also when thinking about microservices. These terms of coupling and cohesion. And typically we talk about the desirable characteristics of our modular architectures, in our case, our microservice architectures. We talk about wanting low coupling and strong or high cohesion. So these are what we would like out of our systems. I'm sure you've heard these terms before, but just to very quickly describe what they are, and then we're going to take a look at them in the context of microservice architecture. When we talk about cohesion, we can kind of think of this as the property that says the code that stays together, that changes together, stays together. If I want to change the logic associated with how I manage an invoice, I would like to be able to change that in one place of my system. I don't want to have to go to 15 different places. So if the functionality you're trying to change is spread all over your system, that's often a sign that you have a system with low cohesion. Systems with low cohesion, they'll tend to take you longer to make changes because you've got to change those things in more places. It can make it harder for you to refactor abstractions. And it also introduces the possibility of bugs because you might make a change in some of the places, but not the other places you want. What we want really is this idea of strong cohesion so that I don't have to go changing the same code in lots of different places. We then have coupling. So coupling is the degree to which things are coupled together. And we want our coupling to be low, especially with our microservice architectures, because we want this property of independent deployability. Coupling is the degree to which changing one module requires you to change another. So in our world, our microservices. So if I have to change one microservice, do I have to change another? If that's happening a lot, that's a sign that I've got a high coupling, and we want low coupling. Another sort of concept that comes out of this space is something called Constantine's law, which is named after Larry Constantine. It's basically this observation that these ideas of coupling and cohesion are linked. A structure is stable if cohesion is strong and coupling is low. In other words, if all of my code is in one place, all sort of the related code is in one place, if I change it, I'm less likely to need to change anything else. Therefore, my coupling will be low. On the other hand, if the functionality around, say, invoicing is spread across my system and I have to change that functionality, I'm going to have to change lots of things together. I also have high coupling. So when we can get cohesion, if we can get strong cohesion, we should also get low coupling and vice versa. Now, cohesion is sort of a bit easy to get your head around in a way. What I find where most of the confusion rises is in the world of coupling, thinking about different types of coupling. Now, when you look in the old books, I've got one of them here. I had to get this on Amazon. A proper copy of Structured Programming by Jordan and Constantine right now costs me about $80 online. This was about $6, which is why I've got it. It's quite good because I found somebody's. It's clearly from a university course because they've got their notes in it from about the 1980s, which shows you how old that book is. But when we go back to a lot of these old books, there were lots of definitions of different types of coupling. And there's a rich sort of set of models out there that describe coupling in the context of computer programs. But we don't really have the same set of language or understanding about those concepts in a microservices world. Because some of those terms don't make sense, right? Some of the types of coupling we describe and have the nuances around the types of coupling, which makes perfect sense when you're talking about a couple of classes interacting with each other within the program, don't necessarily make sense at the microservices level. So what I'm trying to do is to go back and look at the different types of coupling that are coming out of that world and trying to translate them into concepts and terms that make sense for us when we're thinking about service development. So this is not by no means a finished artifact, but I just wanted to share with you 3 different types of coupling and how I see them manifest themselves in a microservice environment and what you can do about them. But in general, remember, we're looking for low or loose forms of coupling. We're going to look at 3 primary forms of coupling today. We look at domain coupling, common coupling, and content coupling. The idea here is that as we go from domain coupling to content coupling, we're increasing the degree of coupling. So content coupling is the worst, common coupling is still bad, and domain coupling is kind of okay. It's a bit of a simplification here. So let's start with domain coupling. Domain coupling describes a situation where one service needs something that another service has. At a base level, this is kind of sensible, right? So in this example here, I've got my order processor. So my order processor needs to do some things with the warehouse and the payment. So the warehouse is where we manage stock. So as part of carrying out an order, I need to reserve stock. The order processor doesn't have that responsibility. The warehouse does. So I go to the warehouse and say, please, can I reserve some stock? Likewise, the order processor can trigger payment, but doesn't handle payment. Payment's done by a separate payments microservice. So I have to go to the payment microservice and say, please, can you place this payment or make this payment? So in that way, our microservice is sort of coupled in a way, right? So our order processor has a degree of coupling to warehouse and to payment. And that coupling is what I describe as domain coupling, because we are coupled at the level of the domain. If you've ever done any sort of looking into REST, you might have heard the phrase domain application protocol. That's kind of the same thing. Some degree of domain coupling is unavoidable in our system. Because ultimately we are building a system which is a bunch of microservices that are collaborating with one another in order to carry out some set of operations for our users. So this collaboration plays out in some form of domain coupling like this. Even so, we can still look to minimize it. Ideally, you will talk to as few services as possible, because that reduces the possibility that there's going to be cascading changes that are going to affect you. If I change the warehouse in such a way that reserving stock is changed, the order processor is also going to have to update to accommodate that. But there's no link or communication between warehouse and payment. Changing how stock is reserved in the warehouse is not going to affect the payment service. So by thinking about who uses what, we can limit the impact of any changes that we might make to our service boundaries. It can also be a bit of a smell if you see a service which has too much domain coupling. Something like an order processor is a kind of name which always makes me think something bad's going to happen, right? This is probably like some orchestrated business process. And you'll often find these kinds of services talking to 5, 10, 15, 20, 25 services. Whenever you see a service that has a lot of outbound domain coupling, it sometimes, but not always, is an indication that that service might be doing a lot of stuff, and it's potentially a space where logic may be centralized. And you might want to look at it as something that needs to be broken apart if it's causing you problems. But domain coupling in general is to be expected and is unavoidable at some level, but you still might look to minimize it. We now move on to looking at common coupling. And common coupling is something that's potentially more rife inside programs than it is between programs, but even between services, but even so, it still comes up quite a lot. With common coupling, we basically have an externally defined common data set that we all make use of. So this could be a shared database. This could be some in-memory data, like an in-memory cache, or some, and specifically here, some shared cache. So in this situation here, I've got a warehouse service. The warehouse service is basically updating some stock levels that are held in, let's say a Redis cache, because we might as well make this cutting edge, right? So I've got a cutting edge Redis cache that definitely won't split brain on me any minute. So I'm putting data into my Redis cache, which is telling people about the stock levels. And I've got other services that care about the stock levels. So I've got the order processor that wants to go and check stock levels before it places orders. And I've got a forecasting service, which is using the information about what's in those stock levels to work out what we need to buy and what the latest trends are. So in this situation, this sort of externally defined data source here, this stock levels thing, we've got lots of different services are using it. And the more structured that data is, the more problematic this can become. The worst case examples of this are sort of a shared database, but even a shared cache can have these properties. You know, if I make a change to that common set of data, that's potentially going to impact multiple services. But these common coupling points also often hide other communications going on that you're not really aware of. So often you'll find that things are really talking to each other via these common global sources of data. This is like having global mutable state in a program, but this is global mutable state across multiple programs. And you can kind of see how that could end quite badly for a number of different reasons. We're now moving on to the worst form of coupling, and that's what we call content coupling, although it does have another name, which we'll get to in a minute. So in this situation, I've got an order service, and the order service stores its data in a database. And like any good microservice, it said, my data is my business. This is one of the ways we avoid a lot of the coupling issues, is if a microservice needs to store or manage data, it treats that as an internal implementation concern, and it doesn't allow people outside to access it, or it shouldn't allow people outside to access it. So along comes the order processor, and the order processor wants to update the state of the order. And so it sends a request to that order and says, please, can you change the state of order 123? The order code can look at that request and decide, yes, that's a good idea, or no, that's not a good idea. It can accept or reject that request. If it accepts that request, it can update the state in the database. But the key thing here is we have a well-defined service interface. We haven't directly exposed our data to the order processor. We just have to maintain compatibility of that interface and all will be well. And that's great. But oh no, we were working late last Friday and someone came along and said, can I just access your database quickly? I promise it won't hurt. And we allowed the warehouse to directly access our database. And now the warehouse is still going into our database directly and updating the state of orders to tell us when they're being picked or when they've been shipped, bypassing our service entirely. So now we're in a kind of a weird world. We've got a set of logic inside the order service that determines how data is allowed to be changed inside our service boundary, but that's also being entirely bypassed. Fundamentally, we've bypassed all information hiding. The moment you allow somebody else to reach straight into your database and grab all your stuff, all bets are off. It now becomes really difficult to know what can be changed easily. Can I add another column? Probably adding another column is okay. Could I remove a column? Don't know. That sounds dangerous. Could I add a new constraint on a column? Well, maybe not. I might not be able to make a column that was previously nullable, not nullable, because the warehouse might be expecting a nullable column entry. So we're now into a world where it's constant guesswork. How would I know what parts of my database that another service uses? Am I going to have to dive through my database logs? Am I going to have to look at the code of the warehouse service to work this stuff out? There's a reason why this form of coupling, where something else reaches straight into your internals, into your data and changes it directly. This type of coupling is also known as something called pathological coupling, which gives you an idea of how bad it is. When you have this degree of coupling, our cohesion also becomes problematic. If we now want to change how order status is affected in our system, we were going to have to update logic in the order process, in the order service itself, but also in the warehouse. The warehouse is now also responsible for how orders are managed. It's just maybe not as clear, but it is there, right? That link is there. So if we add a new status in order, we might now have to go to warehouse to make warehouse aware of that new status and make it aware of what transitions are allowable around that. So we've sort of got now lower cohesion, higher coupling, and we've bypassed information hiding, and we're into a world of hurt. The easy way to fix this: don't have the warehouse talk to your database. Have it come use your service API. That will replace content coupling with domain coupling, and you will be better off. Just to summarize all of that, information hiding is a super old concept, which is super useful. Go back and read that original article from Adrian Colley if you know more about information hiding. And I'm going to be writing up a lot more about the implications of information hiding in the context of microservices as we go. When it comes to coupling, some coupling is worse than others. You can't just say coupling is bad, because that doesn't necessarily make sense. We look at things like the pathological or content coupling. That's a lot worse than just standard domain coupling. And if you can try and reduce your coupling, you're going to be better off. And information hiding can actually play a big part here. But basically, information hiding, low coupling, strong cohesion, all of these ideas, and these are not brand new ideas. These are ideas straight out of modular-based programming. All of these things can make it much easier for us to achieve independent deployability. And guess what? Even if you never build a microservice architecture, even if you stick with your single process monolith, information hiding, low coupling, and strong cohesion will actually make your normal, boring, non-distributed programs better as well. Thanks so much for your time. I've got loads more information over my website. I've got links to free talks and information about upcoming books and all of that kind of stuff out there. And I hope you enjoyed the talk. I think we're going to take a look now to see if we've got any questions that have come up. So let's have a look.
Hello there, Sam.
Hello.
We are, and this is our fault, we're now over time. So
okay.
Push questions to async. Sam is an easy person to find on Twitter.
Yes, I am.
Prolific, in fact. Also, if you want to go to the Brella app and find Sam in there, I'm sure you can send him a message directly. Sam, I'm sorry that we started a little bit late. I feel like we we lost a couple of minutes. Then we
That's okay.
Miscommunication where we thought we were live and we weren't. But I appreciate you fitting it roughly within the time we have available.
That's all right. Well, I know it's been a crazy day. Thanks so much, Mark, for being such a welcoming host. Thanks to all of the lovely people behind the scenes at Software Circus. And I hope you enjoy the rest of the conference.
Thank you, Sam. Very much appreciated. And here's your canned applause to exit to.